Alright, so this is a fun question that turned out to be a headache all morning, but I think it's worked out now. The first thing we want to do is make sure we convert the masses just by dividing by 1,000. That's pretty simple and straightforward. Now, on the other version of this, the other version has the same masses, same spring constant, and then same speeds, just opposite directions. On the other version, it's a little bit easier to do because it has symmetry. And so we can jump right into conservation of energy on the previous question because of its symmetry. In this case, the masses are different, and what that means is that we have to not only do conservation of energy, but also conservation of momentum. And so the trick here is that the energy, the kinetic energy or mechanical energy is conserved only in the frame of reference of the center of mass. So we need to figure out what is the velocity of the center of mass. That is going to be equal to the total momentum of the system divided by the total mass of the system. So momentum-wise, we'll do our first mass, 0.166, times its velocity is 1, plus the momentum of the mass on the right is 0.127, multiplied by its velocity, which is to the left, -1. So we're going to end up subtracting those and then dividing by the total mass of the system, which will be 0.166 plus 0.127. So if I do that, I'm going to get my velocity of the center of mass. That's going to be equal to 0.1331. Make sure that you do not round that too much. We want to try to keep as many digits as possible, at least 4. Okay, now we said the mechanical energy is only conserved from the frame of reference of the center of mass. So we need to convert our velocities, v1, v2, into the frame of reference of the center of mass. So let me change color. So v1 cm is going to be equal to v1 minus vcm. So v1 cm, in other words, velocity 1 in this frame of reference is going to be 1 minus the velocity of the center of mass, 1 minus 0.1331. So v1 cm would be equal to 0.8669. We'll do the same thing for the second velocity. So our second velocity over here for v2 cm, that's equal to v2 v2 minus vcm. Now v2 is negative, so v2 cm is going to be negative as well. It's going to be -1 minus 0.1331. So v2 cm would be equal to -1.1331. All right, so now we're going to do conservation of energy. So we have kinetic energy of 1, and we have the kinetic energy of the second mass. We'll call that K2. And these energies, whenever they collide for a fraction of a second, when we have maximum compression, from the frame of reference of center of mass, those will both look like they're stationary. So that means those energies, the kinetic energies that we have, are going to go into potential energy, elastic potential. So I'm going to have 1/2 kx squared for the first spring, 1/2 kx squared for the second spring. Since we have two springs, that can simplify for us just to kx squared. So let's set this equal to lowercase k for the spring constant x squared. Again, I'm not putting the 1/2 in there because we have two springs. 1/2 kx squared for the left plus 1/2 kx squared for the right. 1/2 plus 1/2 gives us 1. Okay, so let us go from here and start plugging in. So in blue, we have the kinetic energy of mass 1. That's going to be 1/2. That mass is 0.166 times its velocity. The velocity being 0.8669 squared. Then we're going to add on our second kinetic energy. The second kinetic energy, also 1/2. Its mass is 0.127 times its velocity. Since we are squaring the velocity, a negative times a negative will give us a positive. So I'm just going to drop off the negative so we don't confuse anything. So it's times 1.1331 squared. That will be equal to kx squared. All right, so let's clean up the left-hand side. And I get 0.1439. So that's the total kinetic energy of both masses together. That's going to be equal to kx squared, where k is 2210. And then I'm solving for x squared. So at this point, we will divide by the spring constant and take the square root. And so my value for x is going to come out to 0.008069. Oops. 069. Now, that number is in meters, and if you notice, the answer has to be in centimeters. So we're going to take this times 100, and that'll give us our answer in centimeters. And my answer comes out to 0.8069 centimeters. That will be our final answer. And that was a fun problem. There you go.